for approximate nearest neighbor search, which is joint work with Zeshi Chen, my advisor Guy Bloch, Lakshman Dilipilla, Jan Gu, Harsha Vardhan Simhundra, and Vihansa. So, oh, it's not working yet. Okay. Here we go. Okay. So let's start with some motivation. So computing nearest neighbors is a pretty important and well-studied problem in computer science. It's of interest both sort of in the low dimensional regime, specifically where D is 2 or 3. It has a lot of interesting applications in graphics. And it's also very interesting in the high dimensional regime where we're talking about dimension in the range of like 100 to 1,000 with a lot of machine learning and vector search applications. So I want to tell you a little bit about why I started studying this problem. So I sort of come from a theory background, but lately I've been working on this problem from a much more practical direction. So I started working on it in the low dimensional case where there's some really nice theory, had a nice data structure. And then I said, okay, let's work on high dimensions, sort of a natural next step. And I found a picture that, looked, something like this. The algorithms that had actual performance, had actual guarantees in theory, were just being like absolutely mashed into the ground by algorithms of like a very different flavor that did not have any theoretical guarantees. And I've made, in our paper, we make some very, very small steps towards this, as well as some interesting practical steps. But in this talk, I hopefully want to make the case to you, theorists, that these algorithms are interesting. And that maybe you will become this little guy and take up some of these problems and take up some of these algorithms that work well in the practical perspective, from the practical regime, and be inspired to work on them from a theoretical perspective. So let's get started. So just some definitions to start off with. So when we talk about classical nearest neighbor search, we typically have a point set in 2 or 3 dimensions. And we have a query point for which we want to find something like the 4 or 5 nearest neighbors. So here I'm talking about the L2 distance. Typically, like any sort of metric distance, or even in the practical case distances that aren't metrics work, but you can just think of it as L2 throughout the talk. So in this sort of classical setting, we're looking at applications like surface reconstruction, collision detection, ray tracing, other problems in these sorts of graphic space. On the other hand, in high dimensional ANNS, we're usually dealing with high dimensional vectors that are generated via embeddings from some sort of machine learning model. So to give you an example of what I mean, we're encoding objects into points such that objects with nearby points are more likely to be similar to each other, just sort of based on some intuitive sense. So to give you an idea of what this means, here I've shown some embeddings just representing some common nouns, dog, cat, car, ship, sailor, and I've shown some 5-dimensional embeddings. And here the distance between dog and cat is 7. Makes sense, they're like both animals, they're sort of similar to each other. Dog and car are more dissimilar, their distance is 37.48, quite a bit further apart. And then car and ship are also similar since they're both vehicles, etc. So what we're talking about is taking like some sort of object or image or sentence and turning it into some high dimensional vector such that other similar objects have low distance to it. So then the picture, under this setting, the picture I just showed you looks a little bit more like this. So these red points, the points sort of in our base set, represent embeddings of different objects. And the query point also represents an embedding of some sort of object, maybe from the same model, but not necessarily. And when we try to find the 4 nearest neighbors under the L2 distance, what we're trying to do is by finding the objects that are close under L2 distance, we are finding objects that are like intuitively similar to one another. So furthermore, we're doing this in R to the D, where D is around 100 to 1,000. So here we're talking about very, very high dimensions. I believe OpenAI recently went from recently had a new model that went from 8,000 dimensional embeddings down to a measly 1,400. So dimension D is really big here. Any of these algorithms that work by abstracting the dimension to a constant are just not going to be feasible here. And we're doing this in a database of a billion, or even perhaps a trillion points. So I just want to point out here that this means that in real life, parallelism is going to be a necessity. Not just parallelism over searches, which is sort of a like natural intuitive, which is sort of just a natural intuitive thing, just you have a bunch of threads doing searches, but we're also going to have to build this index in parallel. So I want you to just keep that in the back of your mind during this talk. Sequential algorithms are not going to cut it. So furthermore, finding the exact nearest neighbors here might require an exhaustive scan. There's no known subquadratic algorithm for the general case of nearest neighbor search. So we settle for approximate nearest neighbor search. And what we mean by this, so our measure for how good the approximation is recall at K. So this is the fraction of the output candidates that are the true top K nearest neighbors. So if, say, for a single search, you ask for the 10 nearest neighbors and you return 9 of them and the other candidate you return is wrong, you would say that for that data point, you achieve 90% recall. And then typically we'll be talking about recall as like averaged over a larger set of queries. So you'll want, you might have like 10,000 queries and you hope to achieve like 99% recall over the whole data set. So I just want to be clear on definitions before I get into the talk a little further. So here I'm going to use point and vector interchangeably just to represent a point in RD for any dimension D. I'll refer to like the base set or base points. So those are going to be the points that are stored in an ANNS index and are eligible to be returned as answers to queries. So here the query, here we're sort of assuming that the query is not part of the base set. It's going to be a separate vector. Nearest neighbor search or K nearest neighbor search. Given a query point Q and our base set B, we want to return the closest point in B to Q or perhaps the closest K points. And then approximate nearest neighbor search naturally means finding an approximate solution for the definition of recall that I talked about earlier. We'll also briefly mention range search, which is a related problem. Specifically, I think in high dimensions, one of the interesting applications is plagiarism detection. So finding documents that are just a very small perturbation of sort of the original document. So for range search, we're given a query Q and a radius R, and we want to find all of the vectors within distance R of Q. So now I want to,
Quick question. You started with a certain motivation and then you switched to the format of the problem, which of course is very elegant, appropriate as a problem in itself. But if you look at the AI methods, they look at weighted distances. And they sometimes even allow you to connect different dimensions in some way, one way or the other. Here you jump from that to a problem which just looks at all the weights, all the dimensions become equal. So I agree with the beautiful theoretical question here, but I'm just questioning the distance for the invitation.
Well, I guess like in my experience with real world data sets, I think there's a lot of data sets for which the Euclidean distance or maximum or searching for maximum inner product gives you like very meaningful results. I guess I would also say to other measures of distance or weighted distances or things like that. These are definitely things that do come up in practice. And the methods that I'll talk about, they don't have theoretical guarantees for those distances. They do have practical performance though. But like, I think overall to the question of like, is standard Euclidean distance just not relevant here? I don't think that's right. I think
no, I'm talking about the matrix-based approaches that dominate deep learning. And these approaches that classify dogs and cats and car, etc. They are the whole matrix user is inherently structured in the ways that you learn to follow. So you not dismiss that as being curiosity.
Yeah, but I guess here I'm talking about the embeddings that are like the result of these weighted transformations.
The transformation has already been applied. You've already applied the embedding matrix that's learned from the deep learning model, and then these vectors are the things that you get as output.
Yeah.
So this is the range which is the original many parameter and already projected it into.
Exactly.
Yeah. So these embeddings, like, I don't know, this is not really anything about training the model. I already have the model's given me my embeddings, and now I want to do this semantic search.
Okay, thank you.
I should also say, so let me drum up Magdalen a little bit. She worked for a summer and even beyond that at Microsoft Research with Harsha Simhadri, who's like a leading expert on these A&N data structures.
Yeah, no, I'm
And
just
they're-
trying to connect it.
It's used to get like billions of dollars at Microsoft, right? So this is like a pretty important area.
Okay, I'm just trying to make the connection. So
That makes sense. Yeah.
All right. So now I want to give like an overview of some of the current techniques in ANNS. I'm going to start by talking about some of the techniques that have theoretical guarantees, and then I will then we'll sort of move gradually towards more practical techniques and introduce the algorithms. So for a start, early data structures. So we're going to start with a little bit of pessimism. So there's no known subquadratic algorithm for the general case in high dimensions. And most of the existing algorithms that give exact guarantees have an exponential dependence on the dimension D, or perhaps some measure of intrinsic dimensionality. I've shown this picture here to give you like an intuitive sense of why that might be true for a lot of data structures. Because a lot of the exact data structures work by doing something like partitioning the space into a bunch of different buckets, finding a good initial guess. So maybe finding the bucket where the point you're searching for is located in, using that to form like a candidate radius, a candidate ball of nearest neighbors with a radius, and then checking all of the other potential cells that overlap with that radius. So as you can see, like from the geometry of this picture, in 2 dimensions here, that's not that bad. It's only about, I guess that's, yeah, so it's just 8 buckets, it's just 2 to the third. But in higher dimensions, this is just an enormous amount of buckets, and you can't possibly check them all without getting an exponential dependence in a really slow algorithm. Nonetheless, algorithms of this flavor are pretty important in the low dimensional case. So there are a lot of data structures that are either exact or approximate, that use either the true dimension or some measures of like intrinsic dimensionality. One of them is called the expansion constant, and it roughly says that if you have a ball with k points in it and you double the radius you have any ball covering your data set or covering some subset of your data set with k points in it, and you double the radius, the number of points in the larger ball should only be a constant factor greater than the number of points in the smaller ball. Doubling dimension is another similar notion of intrinsic dimensionality. So what I've shown here are a ton of data structures. There's more even than I put on here, that have theoretical guarantees for the case where the dimension is constant, or where this measure of intrinsic dimensionality is constant. And these data structures, I do want to I'm saying they don't work in high dimensions, but I do want to hype them up a bit. They are like state of the art for low dimensions, and data structures like this are used all the time in graphics, like every day. So we just covered a little bit on earlier data structures. So now I want to talk about locality-sensitive hashing, which is kind of a generalization of this idea, for solving nearest neighbors in high dimensions. So locality-sensitive hashing comes under a larger umbrella of what I like to call bucking-based ANNS algorithms. And it's a very, the technique is like something the technique is pretty intuitive. During the build, what you do is you assign each point to one or more, sorry, somebody's a little odd with my animations. What you do with your point set is you assign each point to one or more buckets, where your buckets are something like maybe 50 to 500 to 1,000 points. So you assign points to buckets so that nearby points are likely to be in the same buckets. And then at query time, what you do is you find the buckets that correspond to the query point. So maybe you keep like so maybe you do this via hash function, or maybe you keep like a representative element and compute the closest buckets to the query in terms of those representative elements. So you find the buckets that are near the query, and then you exhaustively scan all of the points inside the bucket, and return the k-nearest points that are closest. So this is a pretty intuitive technique. And it does have some interesting theoretical guarantees in the case of locality-sensitive hashing. Okay. So locality-sensitive hashing is a method that works in theory. And it works by assigning points to buckets via locality-sensitive hash functions. So these are hash functions that that are capable of distinguishing between distances r and c times r, with probability rho, which is proportional to some function of c. So using a hash function like this, it's possible to hash your data set about log n times. And when a query point comes in, you find the bucket that it hashes to, look at all of the points in that bucket, and out of those, you return the k nearest neighbors. And this is known to enable approximate search with cost that's logarithmic in the number of points, or linear in the doubling dimension instead of exponential. There's a lot of varying ways in which you can do this. There's a lot of hash families that are tailored to different distance metrics, hash families that data-dependent hashing that responds to the particular properties of the data set instead of just picking a hash function without knowledge of the data set. Yeah, so two examples are cross polytope hashing, where you use the faces of a polytope in order to partition points into buckets, or using random hyperplanes to partition points into buckets. There's a lot of LSH algorithms out in the world. So originally they were proposed by Indike and Motwani in stock 98 and Charkar in stock 2002. And it's it's definitely a technique that is used in practical ANNS right now. Although we'll see later that it doesn't actually, in a lot of cases, it doesn't actually perform that well. So let's talk about some practical pros and cons of LSH. I'm going to substantiate this with some experimental results later once we learn a little bit about the other competitors. So one pro is that they have pretty short build times compared to other types of ANNS, because all you're doing is creating a hash function and hashing all of your points into buckets. It's easy to reach a billion scale, since again, all you're doing is hashing, and it's naturally parallel. Has limited support for dynamic updates. So by this, I mean insertions and deletions, during the process of querying. So I say limited because by the naturally by the method, you can just insert and delete points out of your hash buckets. But in real life, there's a lot of distribution. In real life, distribution shift might become a problem. So if the point set that you started out with is actually very different than the point set that you end up with after, say, a day of updates, the original hash functions you chose might not work out that well, and you might have to choose. You might have to rebuild it. So this is why I say it's limited. We also find practically good performance on range search. I think this is a pretty natural result for a bucketing-based algorithm, because what happens in a range search is you want to return a bunch of candidates in each bucket. So the fact that you have to actually search through the candidates in every bucket becomes a feature rather than a bug. On the other hand, it's relatively hard for these LSH algorithms to reach high recall for large data sets, because if your buckets don't partition the k nearest neighbor, if you imagine the k nearest neighbor ball If the k-nearest neighbor ball of a particular query just overlaps with a ton of buckets, you'll be left doing an exhaustive search over like tens of thousands of points, which just gets too expensive. We also find extremely bad performance compared to other methods on out of distribution queries. So I mentioned earlier when I was talking about embeddings that the points in our base set are the result of some sort of machine learning model. And the point that we're querying is also the result of a machine learning model, is also like the result of an embedder, but they might not actually be the same one. It's a perfectly valid thing to do to query something that was an embedding of a different model. And we find pretty bad performance, and I'll show you some practical results later on out of distribution queries. They're also called cross-modal queries sometimes. All right, any questions before we continue? Yeah.
Can you give an example of like an application that would have like out of distribution includes?
Oh yeah. So a pretty common one, so I mentioned the word cross-modal. So a pretty common one is cross-modal search. So maybe you have like embeddings corresponding to sentences or phrases, and you want to match them to embeddings corresponding to images. So sort of naturally, you'll have to use different encoders to transform those pieces of data into vectors. Search between like words of different languages is another example. Like if you want the word for cat in French to be the same as the word for to have a close distance to the word for cat in English, for example. Yeah.
Yeah, I have a question. I'm trying to still go to the original motivation. What you say is that you do training, and the training is done. Now you are exclusively in the space of inference.
Yes.
Now, in my mind, this is very confusing because if you are hiding during the training the type of inferencing you are going to do, and you are pulling it out of your sleeve, maybe you would like to inform the type of inferencing you do in the training, so it will prepare you for the type of inferencing you do. Because it appears that, to me, I find it very confusing that there is a wall where the training is done and now we are only in the inference space. It looks to me something methodical, like too incomplete. What am I missing?
So are you saying that, okay, so you're saying one of two things, I'm not sure which. So is it that it feels like cheating to you that you're—
No, it feels like an incomplete methodology, because what is the training for?
So you're saying that what you—
is for proper inference, right? Okay. Now, what you're doing the training, and this was done by a third party before you even start. And the training is done because they had a certain inferencing anticipated. Now, you're trying to consider different forms of inferencing that, had the training been aware of it, it might have produced for you different results. Because it's a closed loop. I mean, you know, that the value of training is only determined on how successful you are on inference. So I think that by separating the two, I see a methodological disconnect. Does it make sense?
Yeah, I see what you mean. I'm aware of, so I guess like, well, I guess one thing I would say is like, I do think that, this is how these things are done in practice. So part of this research is responding to that. But I think there is some work on trying to, like you said, taking the inference task into account when the machine learning model is trained. From what I know of it, it hasn't actually been very, from what I know of it, I don't think it's produced successful results yet. I agree that it seems like an intuitive direction though. All right. So now I want to talk about a totally different technique for computing nearest neighbors in high dimensions, which is graph-based ANNS. So in a graph-based ANN index, what you're trying to do is take your base set of points and form a graph over them, such that points form edges to other nearby points, maybe also some further away points, But what you basically want to do is build a graph such that the edges have some sort of distance relationship between the base points. So I'll maybe first describe how to query the graph, and then we'll talk about how you might want to actually construct such a graph. So these graphs are queried by a version of greedy search. So here we're going to be talking about a graph search starting from this start point S. So this is a base point. And then this blue point Q is a query point for which we're trying to iterate to the nearest neighbor. So what we do is once we get to the start point, we compute the distances between, we compute the distance to Q from all of the out neighbors of the start point. So these are out neighbors in the graph, not like, I know it's a little confusing, the terminology out neighbors. So what I mean is the out neighbors in the graph, not like the nearest neighbors of the start point. So in this case, this point here is the nearest neighbor to Q among all of the out neighbors of S. So we hop to this point, then we look at its neighbors and hop to the nearest neighbor of Q among those, and so on and so forth, until the distance to Q stops improving. And then we return this point, and then we would return this point as the nearest neighbor. And we typically generalize this to a k nearest neighbor search by instead of keeping the top distance, keep like a frontier of say 10 to 20 elements, and go until you can't improve the distance from like the 20th element. So then the goal, sort of given this method of searching, is to create a graph, maybe of around log n degree, because this is probably what we'll have to do to guarantee connectivity. We'll create an O of log n degree graph, and what we want the graphs to be capable of doing is to guide queries with the fewest hops and the fewest possible distance comparisons. So yeah, so is this task clear to everybody? You want to design a graph such that this greedy search procedure is likely to give you the nearest neighbors. Okay. So graph-based ANNS algorithms are probably the most important algorithms for computing nearest neighbors in practice. So here I've shown a very small set of 18 of the algorithms out in the literature. But if you keep reading, papers on these, you'll find hundreds. I do want to note, unfortunately, there's no known theoretical guarantees for any of these algorithms. So we don't actually know in theory how good of an approximation they give. But on existing data sets, they seem to do a very good job. So in our paper, that is partially the inspiration for this talk, we show how to build several of these popular ANNS algorithms in parallel, lock-free, so without the use of any sort of locks, and with full determinism. So parallel, but like I mentioned at the beginning, parallel building is just going to be, since we're dealing with data sets on the range of like 1 billion points on large machines, parallel building is just going to be something that you have to do. Ideally, we'd like to do this without locks, partially because lock-free algorithms just tend to be faster than algorithms with locks, but also because locks introduce non-determinism into the index build. And this is something that is very much, this is something that people do not like in industry pipelines. It's also a barrier to getting theoretical properties like history independence at some point in the future. So what we set out to do was to take these algorithms and say, okay, we don't know how to prove an approximation ratio yet. But what we do want to do is take these algorithms and get rid of all the non-determinism, get rid of all the locks, and just do the best job we can at doing these parallel builds. So now I'm going to cover a couple of techniques for building these graphs, and I'm going to talk a little bit about how we parallelize them. So the first approach is an incremental build. So I'm presenting this generally, but it corresponds to a lot of these ANNS graph algorithms, specifically DiskANN, NSG, HNSW. So it's an incremental build. So it's defined by the insertion procedure. So here we're trying to insert point P. R is the degree bound of the graph, and alpha is a constant greater than 1. You could think of it as between 1 and 2. So how we do this, how we insert into an existing graph, is we take this point P, and we look at the set of vertices that are visited by this greedy search in the initial graph. So this is not the set of nearest neighbors, but the whole set of vertices visited. So here you can see it forms this connected subgraph of the existing graph G. So these are going to be the candidates for the out neighbors of P. So then we apply a prune procedure on this set of visited vertices. I'm going to describe this prune procedure soon, but right now let's abstract it. And after the prune procedure, we've added out neighbors of P, but P is not reachable yet, since no points have edges to P, so we need to make P reachable. And our heuristic for doing this is for all of the vertices that P forms an edge to. We attempt to form, if P forms an edge to little v, we attempt to form an edge from little v to P. And this might overflow. So we've established this degree bound R, which might overflow. So if we overflow the neighbors of little v, we also apply the prune procedure to little v. So this is all well and good, but doesn't really mean anything without the prune procedure. So let's talk about how we prune. So this is for the pruning procedure. So as a reminder, this set V is all of these vertices here that are visited by the greedy search for P starting from node S. So we're going to return a set V prime of the points that are going to be the out neighbors of V. So here, what we're trying to do is provide a graph that has good connectivity and is likely to help the search converge. But we don't want a graph that has too high a degree, because then the greedy search, when you hit a vertex, it will have to look at all of the out neighbors of that vertex and compute the distance to all of them. These distance computations are super, super expensive. They're like 1,000-dimensional vectors. So it's really important not to do this. So here's how we prune. So we start by sorting V in increasing order of distance from P. So here I've shown in order 1 to 7. And at the beginning of the search, we add the closest neighbor to P that isn't already added. So we just take the closest neighbor to P that hasn't already been eliminated by the pruning and add that to P. And then we do the following procedure on the remaining candidates. So if for any V in V prime, the distance between, so for any V in V prime, so that's already been added, the distance between V and VI is less than the distance between P and VI divided by alpha, which is a factor greater than 1 here, skip I and continue. So that might not make a lot of sense. In words. So let's look at an example for where it prunes something out. So it's not going to prune something out for V2. We're going to form an edge to V3. And then what we do when we try to form an edge to V4 is we notice that the distance between P and V4 is greater than the distance between V3 and V4. This is also softened to some extent by this alpha factor. And in this case, where the distance between P and V4 is greater than the distance between V3 and V4, we say, oh, okay, this is an edge that's actually quite likely to already be in the graph. We shouldn't be reaching V4 from P because we can go through V3 instead and reach it in just 2 hops without adding this additional edge. Does that make sense? Okay, I always think this equation is a little bit confusing, but this picture makes it very clear what we're doing. So we continue, we nix this edge, continue this pruning procedure, and end up adding V1, V2, V3, and V4. And we also just stop once V prime reaches the size of R. After that, we just stop and don't consider any other neighbors. Okay. So this is actually, this is the whole algorithm. Nothing, nothing's really abstracted here. One question that I sometimes get asked is, how did you pick a point to be the start? And the answer is that it does not matter, you can pick any point. This procedure is adaptive, this procedure is adaptive enough to, this procedure is just adaptive enough to start, adaptive enough to start from any point. And actually a really funny anecdote is the first time I coded this algorithm, I tried to take the medoid of the data set. So I was like adding all, and I did this by like adding up all of the coordinates and dividing them by n to find the centroid, and then picking the point closest to that and making it the medoid. Sounds very, very fancy. Surely that'll work. But it turned out that I forgot the divide by n step. So I was instead picking like a total extremal point. And then when I fixed it, there was no difference at all. So I really promise you that it doesn't matter. All right. So I mentioned this softening factor alpha here. So putting alpha higher means that an edge is less likely to be kicked out during the pruning procedure. I just want to show you visually that this makes for a much denser graph. So this is a nice parameter that can be used to control the density of the graph. So the question that I want to ask next is, what is the correct approach to parallelizing an incremental build like this? So existing algorithms basically do the following thing. I probably shouldn't have put the answer on this slide right now, but just listen. So existing algorithms kind of do the following thing. They throw all of the insertions into some sort of parallel for loop, and they just like let it go hog wild and they use per point locks on all of the vertices to make sure that two threads don't try to write to a vertex at the same time, or you don't try to read a vertex that's already being written to. So just totally like non-deterministic hog wild. We don't want to do this. Yeah.
Just to clarify, I mean, in the incremental setting or in sequential setting, there's no issue with determinism. Right?
Yeah. So if you're doing this in the sequential setting, there's no issue. This will be fully deterministic. Yeah.
And once we introduce parallelism or concurrency in the way that it's used in practice right now, like there might be issues. Yeah,
there might be issues. I mean, locks both lend themselves to non-determinism, which we don't like. We want to know what the answer, we want the answer to be the same each time. And they can also lead to some performance degradation if you have contention. Yeah.
Do I understand correctly that the structure you get at the end of the day is going to be dependent on the order of insertion?
Yes, that's correct.
Which is deterministic.
So in the sequential case, that would be deterministic. But
parallel, you are parallelizing the sequential case.
Sorry?
When you do parallel, you parallelize the sequential case. So that's the
so what I'm contrasting here, so the sequential case is fully deterministic. And then I'm contrasting the approach that's used in practice of just throwing things in a parallel for loop and using locks for contention control. And then I'm going to contrast this with our approach. Does that make sense?
I'm not sure, because I'll tell you what I'm trying to understand. In many of these general problems, what you're really trying to do, you're trying to find some local minimum. And prevailing methodologies to finding a local minimum is to interject some form of randomization, where it's not deterministic. And it seems that you are going against it. It seems that you have, once you start, you are unwilling to try and different things, and maybe in the spirit of stochastic gradient descent, okay, or many other things. I think that determinism is an advantage, but it also comes at a cost, and you seem to take to be one-sided. It's determinism.
Yeah. Well, whoa, is that a microphone? Okay. One thing I would point out is that you can use like deterministic random, you can use like deterministic randomness in practice. So like you can use an algorithm that you give, when you fix the seed, once you fix the seed, it'll give you a deterministic output. Yeah.
Sorry, so I guess maybe I didn't understand, or the order in which the points are actually being it's a random permutation, right? So there is randomness kind of baked into the ordering, right?
Yeah. So in the static build, what you would do is do a random permutation. But like in the dynamic case, if you're just given a stream of inserts or deletes, then you can't use randomness over the order. So it would probably be bad if the performance of this algorithm was dependent on the random permutation in that way. And indeed, we find that it makes a pretty small impact. Okay. So how to parallelize this incremental build without the use of blocks? So I've had the answer. Unfortunately, I've had the answer up on the slide for like 5 minutes. But the idea is to use prefix doubling. It's a technique from parallel work on incremental algorithms like linear programs to parallelize without the use of blocks. So this is another area where the theory of parallel incremental algorithms is informing our practice here. These aren't algorithms with bounds that we know about, but basically the same technique works. So the idea of prefix doubling is to do the inserts in batches of doubling size. So you first insert 1 vertex, then 2, then 8, and so on until you insert a final batch of n/2 vertices. So these insertions are sort of internally, they're like internally read only. So for all of these like n/4, we run the visit procedure on the existing graph. We do the pruning without modifying the graph. And then we parallelize the last step where we invert the backwards edges by combining all of the back edges from every single one of these batch of inserts and sorting them based on what vertex in the graph they belong to, and then writing to the graph only one time. Does that make sense? So in this way, all of the indices in this group, say of n/4, get to see a graph of size n/4. So they get a lot of, they have a ton of vertices to visit. It's enough data so that they're able to form good connections, even without being able to form internal connections between each other. And we found experimentally that this doesn't really lead to any sort of degradation of the index as opposed to like a sequential build. I mean, it was maybe like 1%, but it really worked very well. I do want to note in practice, we wouldn't be doing a batch of n/2. We would probably be capping the batch size at something a little bit more tuned to our machine. So maybe like 10,000 or 100,000 just to exploit the parallelism of the machine. There's no need to go up to n/2, and it might be it might have some memory problems if you do. Okay, so yes, we're inserting all of these batches. We're running a little low on time, so I'm not going to tell you about, I'm going to skip these next 2 slides about a different approach to building these graphs. So I want to skip to a few experimental results because they're sort of the motivation for doing this work. So this figure is on the parallel performance of our lock-free implementations. So here, the algorithm, the incremental build that I was just talking to you about, based on disk ANN. This is our version of par disk ANN, this blue line. So what we have on the y-axis here is the number of threads going from 0 to this is 96 hyperthreads. And what we have, so this is on the x-axis, increasing the number of threads. And on the y-axis, what we're plotting is speed up relative to the original implementation. So the implementation before we parallelized it on 1 thread. So what this means is that if you look at these gray lines, which correspond to the original implementation, so this is the speed up that the algorithm gets relative to itself on 1 thread. So if I, for this algorithm HCNNG, it gets a 25x speed up once it goes to 96 threads. But then in our implementation, it gets up to a 308 times speed up at 96 threads. So we're able to show pretty significant speed up by rewriting these algorithms to make them lock free. And in particular, the improvement here is basically entirely, this is an example of where the improvement is basically entirely from less contention. With some of these other algorithms, we made some other performance improvements. So let's skip to, so now I want to show you some actual results on how these algorithms do on real world data sets. So this is an example that's showing out of distribution queries. So this is what I mentioned earlier, and one of the cases where locality sensitive hashing or other bucketing based algorithms don't seem to do very well because they're not tailored to the data set. So what we're looking at here is a QPS recall plot. So on the x-axis, we have recall 10 at 10. So we're retrieving the top 10 nearest neighbors. And on the x-axis, we have queries per second. So this would be on a machine with about 196. This would be on a machine with 196 threads. So here, so these three algorithms are the parallel lock-free implementations from our paper. So DiskANN, HNSW, and HCNNG. And then FACE is a bucketing-based algorithm based on clustering, and Falcon is an LSH algorithm. So this is the one that actually has some interesting theory behind it. So as you can see, the curve for the graph, the curve for the graph-based algorithms is, they're both getting like extremely good recall at much higher QPS. One interesting thing that I found here that I didn't actually, one interesting thing I found here that I didn't anticipate is that both of the bucketing-based algorithms actually seem to experience the same barrier in terms of recall. I don't know if this suggests something inherent, but it's something I found interesting. Any questions about this plot? Yeah.
I'm curious, how do you control the number of queries per second? What is changing?
Oh, good question. Yes. So there's a lot of parameters. So the greedy search actually has a lot of parameters. The main parameter is the size of the frontier.
I see.
And for you actually don't, the frontier has to be the size of the number of nearest neighbors you want to return, but it can be a lot bigger. And when it's bigger, it just means you will explore many more vertices. Yeah, sorry about that. Yeah.
Maybe I missed it, but how big of like an index is this query that should affect the queries per second?
Oh yeah, this is a billion.
Okay. Wow.
Yes, big machine, lots of memory. Yeah.
Do you have a comparison with others who try to solve the same problem, or you just try different approaches and compare them?
Sorry, could you say that one more time?
Has anybody before you worked on this problem, and did you make a comparison with them? It appears that you consider different approaches if you compare them one against the other.
So do you mean like, has anybody else taken all of these approaches and tried to compare them?
No,
Or-
just if they proposed anything which they believe is good,
That like didn't make it into here, or?
that you compare them.
Maybe you can explain which of these are not our implementations. And
Oh.
also on the previous slide, there were some that were not ours.
Yeah, so I wanted to show this one because it was out of distribution, but we can also look at, well, I guess it's sort of the same plot. So here, FACE and Falcon are algorithms that we didn't implement ourselves. So they're both bucketing based algorithms, and then these are graph based algorithms which we implemented. And I guess you might ask, like, why do we not show the original implementations on these plots? And the answer is that the original implementations are like not actually memory efficient enough to run at a billion scale. I mean, this is like on a machine with 2 terabytes main memory, and we still couldn't run the original implementations on it. So that's why they're not shown.
Did you try to compare it under the condition that they were?
Under the what?
Under the same condition that they were, did you try to do an apples to apples?
Oh, like compare our graph based algorithms with their original implementation?
Under the same conditions that they advocate.
So I think you showed that in the previous slide, right?
So here's an example of one comparison that we did. So we basically tried to make sure that, this isn't a QPS recall plot. The QPS recall, or the recall that you get for the same parameters, is not that much changed by our own implementations. But what we really changed was the parallelism and memory efficiency. So I can go through this plot one more time. So this is on a machine with 96 threads. So going from building with one thread to 96. And then this is on the y-axis, we have speed up relative to the original implementation on one thread. So this is to say that, you know, for example, here for HCNNG, it gets a 25x speed up at 96 threads compared to what it got at one thread. And then our implementation gets a 308x speed up compared to what the original implementation got on one thread. And this is building these algorithms with the same parameters or as similar as possible.
On the same input.
Yeah, on the same input. Yeah.
Yeah, I guess any different, like you mentioned for prefix doubling, like you might artificially, like you might want to do n-1 to 2, you would constrain it based on like the amount of parallelism you actually have. Are you doing that for these things? Or like, when you vary the number of threads, are you also varying how the prefix doubling?
No, we don't. We basically tuned them all for hundreds of threads. And we don't tune, there's not really much need to tune the parallelism down for fewer threads. It doesn't really hurt you. Yeah, does that answer your question? Yeah, there are some cases where we had to, we had to make like small modifications all to the actual design of the algorithm along the way to scale them properly. Like HCNNG, for example, basically it turned out to have memory, the amount of memory it needed was like linear in the number of threads. So for running it at a lot of threads, we had to take some steps to get the memory down a little bit more, and that modified the algorithm. Yeah, so I guess that's one example where the algorithm design had to change because of the parallelism. Okay, so I want to mention very briefly that there's some pretty interesting new work on the theory of graph-based ANS that just came out, which uses a slow pre-processing version of the algorithm that I described to you today, the incremental build, the big difference between the slow pre-processing and the part I showed you is that instead of pruning on just the visited set, you prune on the entire, every single vertex prunes on the entire set of vertices available in the graph. So this is incredibly, incredibly expensive. But it does have some guarantees in terms of, it shows a guarantee of convergence proportional to log n when the doubling dimension is constant. It also shows, there is unfortunately an exponential dependence in the doubling dimension. But I just wanted to show you that some small steps are being taken to give these algorithms some theoretical grounding. And I hope that this talk has convinced you that maybe you want to take some of those steps yourself too. Okay, thank you. Any questions?
Okay, I'm kind of curious. So you had mentioned that the graph structure depends on the insertion, the order and insertion of the points. Are there any of these, maybe not your algorithm, but maybe any of these other algorithms where the graph structure is an intrinsic of just the points themselves, right? It does not depend on the insertion order.
Just the points. Yeah, so there's one example. So one of the algorithms that we worked on, so it has some randomness, but it didn't depend on like the insertion order of the points themselves. So it basically worked by doing some repeated hierarchical clusterings. Like, so you would split the point set based on 2 random points and split recursively based on whether it's closer to one point or the other. And then it would build a graph at like the leaves of that tree. And that the graph that it built at the leaves was like a degree bounded MST. So it wasn't dependent on, the order of insertion. So I don't know of any that are truly history independent, like that don't rely on either randomness or either like randomness in the clustering or randomness in the input order, yeah. Yes,
Likewise, I'm kind of wondering, so if the graph structure changes, do you have any sense of how that changes actual like accuracy? If the topology of the graph is changing, that may or may not affect, I would imagine, like how good.
yeah, so one place this comes up actually is in deletions. So when you're deleting a vertex from a graph, we definitely, we found that you can, first, you can't just delete the point and delete all of the edges without taking a drop in recall. But also the only thing we found that actually worked to like repair the whole was quite intensive. It actually involved taking the point P with all of its out neighbors. If the point P is deleted, basically introduce all of the points out neighbors to each other. So this is like quadratic in the degree of the graph. So yeah, it definitely matters. I think that that's just an example of one place where it mattered a lot and we really noticed it.
If there's no other questions, let's thank Magdalen again.